Imagine an online store running normally on a quiet Tuesday morning. Then a promotion goes live, a popular creator links to it, or an automated client starts making far more requests than usual. The app itself may be correct, but one running instance has a limit. Its CPU rises, request queues grow, and response time gets worse. Adding more virtual machines by hand can work, but it is slow, error-prone, and difficult to repeat at 2 in the morning. Kubernetes gives teams a different operating model. You declare how an application should run, how much capacity each copy needs, and the boundaries around it. Controllers keep checking the real system against that declaration. In this video, we will follow one web request through the pieces that let a Kubernetes application spread load, add replicas, recover from failure, and scale without treating every spike as an emergency. A Kubernetes cluster separates decision-making from execution. The control plane stores the desired state of the system and coordinates the controllers that act on it. Worker nodes provide the CPU, memory, networking, and storage where applications actually run. When you ask for more copies of an application, Kubernetes does not simply duplicate a process onto a random machine. A scheduler examines the request, looks at the available nodes, considers declared resource needs and placement rules, and binds each new workload to a suitable node. A local agent on that node then pulls the approved image and starts the containers. This division is useful because it makes the platform visible. You can see what you asked for, where Kubernetes placed it, and why a workload is waiting if capacity is not available. A cluster is not unlimited compute. It is a managed pool that makes capacity decisions explicit. The basic unit that runs an application in Kubernetes is a pod. A pod commonly contains one main application container and can include tightly coupled helpers. But an individual pod is not the durable promise. It can crash, be replaced during an upgrade, or move because its node disappears. For a stateless web application, a deployment is usually the durable promise. Its specification says which image should run, how many replicas you want, what resources each replica requests, and how health should be checked. The deployment manages a replica set, and the replica set works to keep the requested number of pods present. If the desired count is 3 and one pod disappears, the controller creates a replacement. This is reconciliation: observe the current state, compare it with the declaration, take a bounded action, and check again. It is why teams scale the replica count rather than babysitting individual processes. More replicas only help if requests can reach them. Pods are intentionally replaceable, so their individual IP addresses should not become your application contract. A Kubernetes service provides that contract. It selects a group of pods using labels and gives clients a stable name and virtual address. As pods become ready, their addresses are added to the service endpoints. When pods stop, fail a readiness check, or are replaced, they leave that eligible set. The networking implementation then distributes new connections across the healthy endpoints. This lets a browser, an internal API, or an ingress layer talk to one stable destination while the backing pods change underneath. Readiness is important here. Starting a container does not prove that it can serve real work. A readiness probe lets an application say when it has loaded configuration, opened its dependencies, or completed initialization. Kubernetes can then avoid routing production traffic to a replica before it is actually prepared. The horizontal Pod Autoscaler, often called HPA, automates the replica count for workloads such as deployments. It regularly reads a metric, compares the observed value with a target, and updates the workload's desired replicas within a minimum and maximum you define. CPU utilization is a common starting point, but it is not the only useful signal. A queue consumer may scale on backlog. An API may scale on requests per second. A streaming service may scale on active sessions. The metric must reflect useful demand, not just a noisy symptom. HPA is also only as meaningful as the resource requests on the pods it targets. If a container requests a particular amount of CPU, Kubernetes has a sensible baseline for interpreting utilization and the scheduler has a clear capacity reservation. When demand rises, HPA asks for more replicas. The deployment and replica set create pods. The scheduler places them. Once they pass readiness, the service can send them traffic. A horizontal Pod Autoscaler can ask for 10 replicas, but it cannot create CPU or memory out of thin air. Each pod has to fit on a node. When no node has enough allocatable resources, new pods remain pending. That is a useful signal, not a mystery. Check the pod events, its requests, placement rules, and the cluster's remaining capacity. In cloud environments, a cluster autoscaler or a managed node provisioning service may add nodes when pending pods justify it. The exact mechanism depends on the platform, but the two loops solve different problems. HPA changes the number of application copies. Node autoscaling changes the pool of machines those copies can run on. Both loops need safe limits. A maximum replica count protects downstream databases and budgets. Node limits protect infrastructure cost and control plane capacity. Scaling is a design decision across the whole request path, not just a button that makes more pods. Autoscaling is only one part of availability. A cluster also has to respond when an application copy becomes unhealthy. Kubernetes supports several kinds of probes with different meanings. A startup probe can give a slow application time to initialize. A readiness probe tells Kubernetes whether a pod should receive service traffic. A liveness probe can indicate when a stuck container should be restarted, although it must be configured carefully because an aggressive probe can cause avoidable restarts. If one replica fails readiness, the service stops routing new traffic to it. If a pod disappears, the replica set continues working toward the desired count and creates a replacement. This does not make every architecture resilient by itself. A single replica, an overloaded database, a broken dependency, or an incorrect health endpoint can still cause downtime. The value is that failure handling becomes observable and repeatable. Healthy copies keep serving while controllers work to restore the declared state. Here is the complete picture. Clients use a stable service instead of chasing individual pod addresses. A deployment declares the application template and the number of replicas it needs. The horizontal pod autoscaler watches a chosen demand signal and adjusts that number within safe boundaries. The scheduler places each new pod on a node with enough capacity. If the cluster has no room, a node autoscaling mechanism may add machines, subject to limits. Readiness checks ensure that only healthy, prepared pods receive new traffic. Controllers replace missing pods and keep reconciling until the running system matches the declaration. The practical next step is not to copy a generic configuration. Measure the demand signal that matters to your app, set realistic requests and limits, test a traffic increase in a safe environment, and inspect what happens when a pod or node fails. Kubernetes is powerful because these pieces work together, but reliability comes from choosing and verifying the right contracts.